In this video, I'm going to begin talking about how you deal with big data across a distributed system and then how to aggregate that data to collect particular information from the database that you have distributed. So as we have big data, it becomes apparent that we need a different storage mechanism. So instead of storing everything on a single server, what is happening now with big data is that you're distributing that storage across multiple servers. So you're creating a distributed system that works together. All of the servers work together to produce this ability that you might have to query the data across all of the servers. So this first video in this series is going to talk a little bit about Hadoop. Hadoop is a distributed architecture that was invented several years ago, and this is the logo for Hadoop. And it comes from the need of big data to be distributed across multiple servers. So it was invented in 2002 at the University of Washington. It was originally known as Nudge, but it was revised to become Hadoop after the publication of several papers from Google. In 2003, the Google file system was introduced, and I'll talk a bit about the Google file system and how that affects Hadoop, as well as their paper on MapReduce, which we will get to in another video. So Hadoop then became, in 2006, an open source project under the Apache Software Foundation. And then it also became a lot more popular. So it provided storage and analytics for companies like Facebook, LinkedIn, Twitter, Netflix, Etsy, and Disney. So it is very popular in the way that it stores data and the way that you deal with that data. So all of these sources, Facebook, LinkedIn, Twitter, and so forth, use Hadoop to store their big data systems. So a bit about Hadoop history. I've already mentioned the Google file system, which came up in 2003. So just a few words about the Google file system and how it works together. So Google determined as they were spidering the web or crawling the web for links that they would need a different storage format so that their searches could be even more efficient. And what they did was they developed this Google file system that took what was a single system and then distributed across multiple servers. So in their Google file system, you have two types of servers. One is a chunk server that stores a fixed size chunk, and then a master server that stores the metadata about those chunks. So the master server is like the pointer to the chunk server. So in the Google file system, a chunk is a large part of a data file, usually about 64 megabytes. And this might not seem like a lot, but on a standard hard drive, a chunk of a file is normally much smaller in the kilobyte range. So assigning a unique 64-bit ID by the master node, a chunk can be uniquely identified. Then the mappings of chunks are maintained by the master server, and then they're replicated several times throughout the network for redundancy and for backup and so forth. So whenever you need to update a particular file, updates happen by a master server granting a limited time release to do an update. The primary chunk server that has the file, the main copy of the file, performs the update, and then it propagates that update to the other servers that contain that file. the change is not committed until all of the chunk servers acknowledge that complete, that they have completed the commit. Now, what this should probably sound like is the two-phase commit protocol, where you have a central server that sends out a request to commit, and the master server serves its role here. And then the primary chunk server then takes on a secondary role of propagating that commit to the other servers containing that file. So here's a picture of the Google file system. On the left, you have an application that is using the file server itself. The chunk mappings are given to the application, and then after the mapping is provided, then the application has direct access to the chunk server rather than having to go through the master server. And this is similar to a broker style architecture where the master serves as the broker to determine where it needs to go, and then it gives direct access to the chunk server. So the chunk servers here contain the files, and they are related to one another so that they can propagate the updates when those updates occur. So the master server keeps track of which chunk server has the main copy of a particular file. And you notice that the files here, file 1 is redundant, file 1 chunk 1 is redundant, file 1 chunk 2 is redundant across all three servers. And then file 2 chunk 1 is redundant. So the redundancy is built in for fault tolerance, so that if you lose information of one server, so if a server goes down, another server can simply become the primary node for that particular chunk. So the master server coordinates everything, and you see this idea of shadow masters. And those shadow masters have the same ability to come online if the master goes down. So the Hadoop distributed file system, often shortened to HDFS, is kind of a very similar product to the Google file system. So it is a system for distributing large data sets across the network of commodity computers. And that's important because when Google came up with this Google file system idea, they were simply running commodity computers, just off-the-shelf computers that you could buy at your local store, and then using those as servers for their needs. So Hadoop is also designed to use a network of commodity computers. It can be complex, and it can manage distributed file components and metadata, but it can also be used on a single system. It also provides a high level of fault tolerance, supporting parallel processing for faster computation, and this is also important in big data. When you have data that's replicated across servers, then it's much easier to perform local operations on those servers and then move those operations, move the results of those operations back to the thing that's collecting those results. So instead of chunks in the Google file system, in Hadoop you have what is known as blocks. So blocks are the same idea as a chunk. You have a file that's divided into subcomponents, and then those subcomponents are known as blocks. The default size in Hadoop is 64 megabytes, but sometimes you can set it up to a higher level than that. The advantages of having such a large block size is to support things like streaming and sequential data access. So if you're Netflix and you have a movie that is streaming, it's more beneficial to you to stream large chunks of data at a time, large blocks of data at a time. And it minimizes disk seek time for file retrieval. If you are looking for 64 kilobytes of information all over a disk, that becomes compounded when you're looking for 64 kilobytes all over a replicated system, a replicated distributed system. So it minimizes the disk seek time for the file retrieval. Then it leads to a faster sequential data access. So again, because of the streaming, it supports the streaming, so you can get a lot more information at one read than you could in a traditional file system. But one point, Hadoop is very bad for random access. So if you're looking on a disk and you have that disk fragmented, then Hadoop is not a good choice for this because because of the way it's designed. It's not designed for small data, it's designed for big data. So some terminology here with Hadoop and the HDFS file system. Blocks in a data set are used to form an HDFS cluster. So a cluster has a couple of different types of things. They have nodes and they have racks. A node is just simply a single computer, and a node contains some of the data, and again you'll have replication. But a rack is actually a collection of 30 to 40 nodes on the same physical network switch. And why is that important? Well, again, it's speed. When you have 30 to 40 nodes on a single switch, then that gives you the ability to quickly transfer data between those nodes. And then a cluster is just a collection of racks. So blocks are stored in data nodes. So this is the same idea as a chunk server in the Google file system. So data nodes are the equivalent of a chunk server. And then a name node is the equivalent of the master node or master server in the Google file system. So it's used to store metadata about the data nodes so it knows where everything is. So fault tolerance is important when you're distributing data across a set of servers. So what happens in HDFS is that it automatically replicates blocks. So by default, 3 replicas exist across 2 racks. And one replica in one rack, one replica exists in one rack and 2 replicas exist in a different rack. And the reason for that is that those replicas are in case that network switch goes down. So if a particular network switch goes down, it wipes out the entire rack. So you still have a backup on another rack with the hopes that they don't both go down at the same time. So HDFS uses what is known as a pipeline to link the replicas together so that you can easily traverse from one replica to another replica. And then the number of replicas can actually be increased. So 3 is default, but you can go up to a higher set if you want. This picture shows an HDFS cluster. So here we have a data set, and that data set has 3 chunks. We have an HDFS cluster here shown with 3 racks, and then each rack has 4 nodes on it. So notice here that you have file B1 in the data set. B1 is stored on node 2 of rack 1. It's replicated twice on rack 2. And again, if this were to go down, then you could bring up rack 2 and access the data just as well. B2 is primarily on rack 2, but it's replicated twice on rack 3 in nodes 1 and 2. And then B3 is primarily in rack 3, but it's replicated in rack 1 twice. And again, all of this is for fault tolerance so that the data set can be accessed even if a network switch physically goes down.